long-range prediction about what's going to happen to the universe. So eventually all the stars are going to run out of fuel. It's going to happen. We only have a finite amount of energy. We have a certain amount of mass. That's it. And so when this actually happened philosophically in Europe, and we realized that the universe is ultimately fated to die basically cold, okay? Eventually the stars are all going to run out of fuel, and they're going to, instead of like reversing the process, instead of starting where the stars blink on and you start to see stars form, now the stars eventually are going to start to fade out because they're going to run out of fuel. They're going to run out of hydrogen, and the stars are going to start to fade out, and eventually the universe is going to kind of turn cold and dark. And this actually kind of threw a pale over all of the philosophy, and even influenced the art that was happening in Europe when they figured all of this out. And it was like, it's kind of depressing. You know, the universe isn't going to last forever. You know, the universe is kind of fated to die out. Our sun is about 5 billion years old. We got about another 5 billion years, give or take, I don't know, maybe 10, 15 minutes, somewhere in that neighborhood. But eventually our star is going to run out of hydrogen. But now, the star is going to get, our sun is going to get bigger and bigger and bigger before that, and eventually we'll all be encompassed with it. That's a long way away. Don't sweat it. Believe me, allowing for what's going on with the coronavirus and everything else, we have a lot other things to worry about. What's going to happen with our star way down on the list, okay? Way down there. Don't even think about it, okay? It would even kind of flip you out even more. So, but it is, I mean, so that's kind of the fate of the universe. So nature has kind of gone in this cycle of the Big Bang, and you have this hydrogen, and that coalesced, and you started the stars, and the stars began to explode, and then, you know, then how did we get like the heavier elements? Because that process only gets you to like iron. So the only way that you could get even more massive gold, silver, and all the elements past that is basically where you have neutron stars collide, and then that's an even more energetic explosion, and that's how you make even like the heavier elements. So literally, it's very philosophical, but we are all made of stardust. Okay. All right. So when you get into, and this might be a good place to, well, we'll get there eventually in about 40 minutes, and I'm running out of fuel. Speaking of which, okay. So when you talk about what's known as positional entropy, and this will allow us to at least predict the sign of the entropy. We might not be able to actually calculate it, but at least we can figure out the sign. So if you look at something that's a solid, okay? So if you look at this table, again, there's a lot of things that I worry about when I walk in this room. I don't worry about this table turning like into a squirrel. Okay, that would be really weird if it did. I've had this table since the fall of 1994. Okay, so I've had this table almost 26 years. Okay, that's 26. What, about 8 years longer than you all have been on this earth? Okay, yeah, that's a scary thought, isn't it? But that's how long I've had this table. And guess what? It's still a table. But that doesn't mean that this table doesn't have some entropy. It does. On an atomic level, there's some things that are moving around. You have protons and neutrons in the nucleus, and that nucleus is vibrating just a little bit. Obviously, you have electrons that are moving around, okay? Because if the electrons weren't moving around, it wouldn't feel solid. So on an atomic level, there is some entropy, but just not very much. Now, if you compare that to a liquid, okay? So if again, I'm not going to do this, but if I poured out my Dr. Pepper, that liquid would flow, but it would still stay stuck together, okay, like water, okay, any liquid. So it moves, it has more places that it can go, but yet it's still kind of stuck together. So it would be like, hey, you know, you go off to college, but you still stay with your friends from high school. So you don't completely break free, but you're going to be moving around, but you're still kind of tied together. Now, The whole key to this also here, this is going to be the big one, and that's why I put on here, okay, all these arrows here. Gases have a tremendous amount of entropy relative to liquids or solids, certainly, okay? So when something is a gas, I mean, it's like, it's free, okay? It's like second graders, a room full of second graders named Timmy, who are completely hyped up on sugar and have no control whatsoever. You talk about a high state of entropy. So if you look at this in terms of like second graders, so this would be the second graders, the solids. They're sitting at their tables, they're their desks, very organized, teacher's very strict. Timmy might fidget around a little bit, but basically we don't give Timmy much of a chance. Now, this could be like a liquid. So let's say, for example, they are going down to the lunchroom, but they make them hold hands as they're going down to the lunchroom. Obviously, you can't do that now because of social distancing, okay? But let's just say. So they can move down to the lunchroom. They're still going to be holding hands, but they can move around a little bit more. Now, as a gas, Timmy is completely on his own. They are outside, it's 80 degrees, Timmy has had sugar, it's the last day of school. These kids are just completely out of control. Huge amount of entropy, a huge amount of disorder. So, when you look at a comparison, this is one of the things that you've got to be able to do, okay? Is look at this and say, okay, which one's going to have a higher state of entropy? So you could have 1 mole of hydrogen at 1 atmosphere or at 5 atmospheres. Okay, so this is a measure of this pressure. So at 1 atmosphere of pressure, okay, versus 5 atmospheres, this is going to have the higher entropy. Because at 5 atmospheres of pressure, these particles are moving around more, okay, and within the sealed container, at that 5 atmospheres of pressure, it's like we're keeping pressure on the class, okay? With more pressure on that class, they're not going to be able to move us around as much. With lower pressure on that class, they're not going to be able to move us around as much because of the fact that, or they will be able to move around more because we've decreased that pressure. You got 1 mole of hydrogen gas at 5 Kelvin or 100 Kelvin. Now, and this is looking at 2 different things. Here we were just looking at pressure, here we were looking at temperature. At 100 Kelvin, that's going to be at a much higher temperature. So this is like Timmy overloaded with sugar, and this is Timmy on a very, very cold day. So this is Timmy overloaded with sugar and it's 80 degrees outside, okay? That's at a higher temperature. Timmy's going to be bopping around a lot more. That's going to be a much higher state of disorder than if Timmy is here on a cold day. So, solid carbon dioxide versus gaseous carbon dioxide. Solid carbon dioxide, otherwise known as dry ice, okay? It's a chunk of dry ice. It's locked into solid. They're going to vibrate a little bit, but not much. Versus gaseous carbon dioxide, this gaseous carbon dioxide is going to have a much higher state of disorder, much higher state of entropy than the solid carbon dioxide is going to be. Okay, so let's look at, here's a good stopping point for today, kids. We're just going to stop right here. And we'll continue more into this tomorrow. Yeah, because that's a lot. We'll finish this up tomorrow. Okay. So let's say salt dissolves in water. So you've got this ionic structure of sodium, chlorine, sodium, chlorine. Okay? And they're bound together and there's a certain amount of energy. And we'll get into lattice energy later. Lattice energy is how much energy it takes to break the bonds that hold these things together. So when salt dissolves in water, you're going to increase the entropy of the sodium and the chlorine, mainly because of the fact that those are no longer bound together. Okay? But this is where you have to look at 2 sides of the coin. So from the sodium and chlorine perspective, that's going to have an increase in entropy because they went from being locked together to being able to move around. But these are going to bound up with water molecules. Okay? Now the water molecules, from their perspective, the water molecules' entropy actually decreases because now they've got these ions that they have to drag around. So this is somewhat analogous to going out on a date. So this is, let's say for example, you know, here's your little brothers and sisters and they're at home, okay? They don't have much entropy. Mom and Dad are going to turn them loose and they're going to let them go out in the house. But you have to take them with them. So you're like the water molecule. So your entropy is actually going to go down because you can't do as much, you don't have as much freedom because you've got to take along little Timmy. So from the sodium and chlorine perspective, when you dissolve it, their entropy increases. The water molecule entropy actually goes down because they're now bound up with these ions that they have to take with them. So it's a matter of perspective. Iodine condenses from a liquid into a gas. Okay? Anytime you go from a gas into a liquid, you're going to greatly decrease that entropy. Because as a gas, okay, it's bopping around, okay, you've got all this energy, and then you're going to make it calm down and go into a liquid. Well, that's going to decrease that entropy. So that's going to have a negative delta S. This would have a positive delta S, okay, from the salt perspective. I just want to make sure we're cool with that. A precipitate of silver chloride is formed from the solution. Now again, if you remember what's happening, that silver and you got chloride ions, and they're bopping around out in the solution, and those are going to bond together and they're going to form AgCl. Okay? So from that perspective, their entropy, again, is going to decrease because they're going to go from these silver ions that are floating around into a precipitate. But again, from the water's perspective, the water's going to be going, God, thank God, now I don't have to drag around this stupid silver ion. I'm going to have more entropy. But strictly from the formation of the silver chloride precipitate, that is going to decrease the entropy because of the fact that you're going from those silver ions into a solid. Okay, I've been talking for an hour, and that's more than enough, especially since I'm out of practice talking to this long. So tomorrow we will finish up this big lecture, and I will get that out to you. So happy Earth Day. Go do something good for the Earth.